Just to start with a brief introduction. So over the last several years, we have found that there are new connections between entanglement, quantum information, and condensed matter theory on one hand, and on the other hand, quantum field theory and the field of holography, which is originated from black hole physics and is meant to be a property of quantum gravity. So there is a sort of kind of overlapping regions. So in this talk, what I would like to do is I would like to give you some introduction about this topic, starting from introducing this concept of holography. So I will assume in this talk that you have some general familiarity with quantum field theory, although I will still introduce the main concepts and also some general familiarity with entanglement. And my aim would be to introduce holography and see how all of this fits into one framework. Okay, so let's first start with holography. What is holography? So the holographic principle was introduced about 40 years ago by Prof and Susskind in this period of 92 to 94, and states that gravity can be described in terms of a theory without gravity, but in a sense in one dimension less. So to put this in pictures, this principle implies that something like the motion of Newton's apple in 3 dimensions should be described or should be captured mathematically by a theory that lives in 2 dimensions, some sort of kind of flatland theory with no gravity. And the dual quantum field theory is associated with the boundary of this 3-dimensional world. So it's like thinking again, this is the apple falling and Newton, and then you have a theory at the boundary of space. And just by formulating a theory in the boundary, you can describe everything that happens in the interior. So one question that we will address in this talk is how do you actually make this sense mathematically? So this idea that this holographic principle originated by thinking about black holes. So if you try to combine general relativity and quantum mechanics, you really have to start, if you want to see what are the right notions, you first have to go into the places where you really need both of them. And this is places where you have objects which originate from general relativity, but also you're in a regime where the gravity is very strong, and you go towards a singularity where you really need a quantum mechanical description. So there are 2 such places. One is about black holes that have a singularity in the interior, and the other is the beginning of the universe. So we're going to start with black holes, and we're going to end this talk with the beginning of our universe. So one of the things that was known since the 70s was that black holes have an entropy which is proportional to the horizon area in Planck units. And the other thing that was also appreciated over the last 50, 60 years is that black holes, you should think of them as the objects which are the most dense objects you can have. So the second law of thermodynamics then implies that black holes maximize the entropy in a given volume. But this is in contrast to what we have with normal material. So normal material, usually the entropy is an extensive quantity. So if you have a quantum field theory or we have some matter system, then its entropy scales proportional to the volume that this object occupies. But in black holes instead of having that the entropy would scale like the volume that the black hole occupies, scientists found that the entropy scales like the area. And therefore, that if you want to match the degrees of freedom, so the degrees of freedom of a quantum gravitational system should behave like the degrees of freedom of quantum field theory with no gravity in 1 dimension less. So that's how the idea was originally formulated. Of course, this doesn't really, even though it is a very kind of deep idea, doesn't tell us exactly how the laws of physics would be formulated if they are to be holographic. So in this talk, my focus would be to review work on the holographic dictionary, how holography works, and in particular to describe its relation to quantum information. So holography has been studied with many, many different goals, starting from describing strongly coupled quantum systems, try to understand how space-time, how space and time emerges out of quantum field theory dynamics, to exploring quantum properties of black holes and cosmology. So this is a topic which is in the mainstream of high energy theoretical physics. There are about 20,000 papers since the paper on ADS-CFT that I will review in the next few slides. It's a topic that encompasses many different areas. So what we will do today is, so the first part will be about the holographic dictionary. So I'll try to explain what it means to have a universe which is described holographically and how you're going to go about formulating the laws of physics. And then we're going to move on to describe the relation between holography and entanglement. And this is going to move us to quantum information. And then we're going to kind of wrap this up by putting kind of sort of a little bit of a bigger picture by describing, going back to the beginning of the universe and describing early universe cosmology using the ideas of holography. Okay, so let's start from the beginning. So the main example of holographic theory is via the so-called ADS-CFT correspondence, which was proposed in 1997 by Maldacena. And this says that quantum gravity in d+1 dimensional under de Sitter spacetime is equivalent to a d-dimensional theory, which is a conformal field theory. So here in this diagram, I describe the spatial sections of under de Sitter. So under de Sitter is a spacetime that has constant negative curvatures, and the spatial sections, you can think of them as a hyperbolic plane, and hyperbolic plane is illustrated here in this illustration by Escher about the angels and the evils. So you can see, so you have exactly the same figure as you move on, because the notion of scaling, there is a notion of scaling in hyperbolic space, which underlies the structure of the space-time. So now, if I now draw again the same diagram, but now, so the spatial slices I have here are the constant time slices in this diagram. So you can think of under de Sitter as some sort of Kahn soup diagram, where you have in each constant time slice, you have one of these hyperbolic planes, and time runs upwards. And the boundary of the space, even though in this diagram it appears as if it's a finite distance, actually it's an infinite distance. So you should think of this more like a Penrose diagram. So you have a conformal boundary that at the end of the space-time, and that's exactly where the dual conformal field theory lives. So it's useful to split the space-time coordinates into a radial coordinate that takes you all the way to the conformal boundary, and some boundary coordinates that parameterize where you are on the boundary. Now, the only thing which is required to set up the correspondence between under de Sitter and conformal field theory is that you have appropriate boundary conditions at the conformal boundary of under de Sitter. So inside the space-time, this can be arbitrarily complicated. It can have black holes, it can be very quantum, and so on. And then we'd like to understand how to extract the physics about the deep interior of the space-time by analyzing the conformal field theory that lives on the boundary of this space-time. Okay, now to explain how to do this, I first need to explain a little bit the notion of duality. So what the words that one uses is that quantum gravity in t+1 dimensions is dual to a conformal field theory. And when we use the word dual, we mean that there is a precise sense in which the two theories describe one and the same object. So it is two different views of the same object. So if you have two different physical theories, then for them to be dual, there must be a map between all parameters and observables from one theory to the other. And there should also be some precise computational framework for dynamical computations on both sides. So if I want to understand something that happens in the deep interior of under de Sitter, I should be able to tell you what this corresponds to the in the boundary theory and what sort of computation I need to do in the boundary theory in order to understand that dynamical question. So the term duality is not used only for holography, and historically it comes all the way back to the beginning of quantum mechanics. So you have the wave-particle duality, but it is a terminology which is quite central to modern theoretical physics. For instance, there are many dualities between supersymmetric theories. And again, one needs to have a similar map like what I describe over here. So now to describe the map between quantum gravity in ADS and quantum field theory, I first need to tell you a little bit about how to define a quantum field theory. So usually the definition of quantum field theory involves a set of fields, which here I would call collectively as phi I, and the Lagrangian that describes the classical dynamics or correspondingly Hamiltonian. So this Lagrangian would depend on these fields and on some other parameters like the masses of the fields, the coupling constants, and so on. And then when we discuss the quantum mechanics of that theory, we would also like to understand, usually we discuss perturbative quantization around some vacuum. So we need to specify which vacuum. For instance, is it a trivial vacuum, or do you try to quantize around the condensate where some of the fields acquire expectation values and so on. So this is some pieces of data that you need to give in order to define the theory. So if there is a dual formulation, you have to be able to provide the same data now in a different way. Now, this is usually how we're discussing quantum field theory in textbooks, but actually there is a somewhat more general formulation, which is a little bit more appropriate in this context. Most of the theories we're discussing are gauge theories, and the actual observables are gauge invariant operators. So instead of discussing elementary fields, we'll be discussing a set of gauge invariant operators. And then these gauge invariant operators, they have certain correlation functions between them. And that might include one-point functions if one has happened to be in a one-digit theory around non-trivial condensates. And furthermore, there may be a moduli space of theories having different vacua and so on, all of them characterized by one-point functions. And in general, the couplings of the theory, the M and G and so on, this would run with energy scale. So we need to be able to account that also in any dual formulation. So to summarize, any dual representation of quantum field theory should include how the parameters and vacuum expectation values are represented, and how gauge invariant operators are represented, and how correlation functions are computed. If you're able to provide those, then you can you have a dual representation of the same theory. Now, examples of observables or commutables are given here. So the most basic example are correlation functions of local operators, like endpoint functions. For example, one basic operator, which is going to play a prominent role in this talk, is the energy momentum tensor. That's the tensor that includes the information about the energy and momentum of a given excitation. Or if you have a gauge theory, you can have Wilson and Topf-Polyakov loops, which are characterized by a path and a gauge group representation. Or you can also have discuss the entanglement entropy, which is something which is associated with the partition of the Hilbert space of the theory. So this is certainly something which is computable. It is not completely subtle whether it's actually observable. So evidence for holography follows from matching the analytic extraction and precise values for these type of observables. So what I will do in the next 10 to 20 minutes is try to explain how to do the matching for these local correlation functions. And then when we move to the part about quantum information, we'll start by discussing how to do the matching about the entanglement entropy. Okay, so now so I gave a general introduction about what is quantum field theory and what are the main objects I would like to match. So now let's go back to the prime example of holography, which is the ADS CFT correspondence, and discuss how these issues are addressed within that framework. So this framework was the precise the dictionary was already proposed very early, shortly after Maltasana's paper, in two papers, one by Kupsa-Klebanov-Polyakov and another by Witten. And it goes as follows: says that for every gauge invariant operator of the quantum field theory, there should exist a corresponding bulk field, which we would call phi. Now, this phi is a field in under de Sitter that has a conformal boundary. So this means that we need to specify boundary conditions for that field. And it turns out that the boundary condition is a field itself. So the boundary conditions for the field phi are parameterized by fields which I would call phi naught. And then the dictionary that they proposed was that this object here has a dual meaning. So one is as a boundary condition for the field phi at infinity, and the second is as a source for the dual gauge invariant operator. Again, recall from the first part, we know that for every operator we have a corresponding field, then the boundary conditions for this field phi naught acts as a source for that operator. And then, so that gives this maps, in a sense, the kinematics, tells you how the variables between the two sides are matched, and then the last bullet point is about dynamics. Now, if you compute the bulk partition function as a function of the boundary condition of this field phi naught, then this is now identified as a generating function of quantum field theory correlation functions. So in the next 5 to 10 minutes, I'll try to unpack this a little bit more. For instance, if you consider as an example scalar fields, then this last bullet point to linear approximation maps to the following defining relation. So on the left-hand side, we have the bulk. So the bulk would be described by some gravity theory. If it is supersymmetric, it would be a supergravity theory. And certainly the original examples was supersymmetric. That's why I put here supergravity. So then the on-shell value of the action as a function of the sources is identified with the generating function of quantum field theory correlation functions. Okay. So how do I actually implement this? So we need to try to compute. So the next few slides, I'll try to explain how to go about computing the left-hand side and how this is going to give you correlation functions of gauge invariant operators. So the first step is to try to analyze the structure of the field equations close to the conformal boundary. And there is a general result that, so if you have a massive scalar field with mass m, this would correspond to an operator of dimension delta. And then the structure of the field equations close to the conformal boundary is given by an expression of this form. So it has two pieces. One is phi naught, which is the boundary condition we need to specify. And then in terms of this, all terms up to this red piece are determined in terms of local equations, in terms of phi naught. And at this order, there is a new piece of data that appears. Okay, so now we know the structure of the field equations near infinity. Then we can go back and evaluate the on-shell action. So here I give, so G here is the metric of ADS. So I have a kinetic term and some potential term. But now, if you try to evaluate this naively, you would find that this is infinite because under de Sitter has infinite volume. So here, in a sense, you have an infinite volume, and you try to evaluate that on shell, and that's infinite because of the infinite volume of space-time. So we need to make sense out of this. So, and to make sense out of this, we're gonna regularize this integral by restricting the radial coordinate to be up to some value epsilon, which is a small number. So we go close to the conformal boundary, but not exactly to the inside the conformal boundary. So now if we take the solution we just computed here and we plug it in our expression, we find that the on-shell value of the action has a behavior of this form. And for generic values of delta, then these terms diverge. So here I organize the terms from the most divergent to less divergent and so on. So the divergences depend only on phi naught. I think the square here is a typo and its derivative. So it turns out that all the divergent terms depend only on the source, but it doesn't depend on these terms. So only the finite terms depend on this one. Okay, so we try to, there was a proposal about holographic duality, but if we try to implement it, then naively we find that this is infinite. So how do we deal with it? Now, this infinity is not really surprising at the end of the day, because if we try to do a quantum field theory computation, we would equally find infinities. But this time, the infinities comes because of ultraviolet issues, because we go to high energies. And this is true even when you have conformal field theories. When you look at correlation functions of gauge invariant operators in conformal field theories, you still get UV infinities. So the infinities that we found on the gravity side over here are just the exact analog of the UV infinities that you have on the quantum field theory side. And the fact that this volume divergences exactly match the quantum field theory divergences is a very strong structural support for the duality. So since the gravity theory behaves as if it is a quantum field theory in one dimension less. But now once we identify the infinities, we know how to, and found the relation with quantum field theory, we know how to deal with them. We can deal with them the same way we deal with in quantum field theory. So in quantum field theory, if we have a regulated quantity, then what we want to do is we want to add counter terms to our quantum field theory such that the infinities are cancelled. And these counter terms should not upset any of the symmetries of the theory. For instance, they should be covariant, and they should also be local. If we allow for no local counter terms, we could trivialize any theory. So we want to borrow from this idea. We want to be able to do the same in ADS. And it turns out that this works exactly the same way. So the analog is to add counter terms, which are defined in the boundary of ADS, and we fix the coefficients such that the divergences are removed. So then we define or normalize on-shell action as a limit of this regulated on-shell action plus the counter terms, and then removing the regulator. So then once we define this quantity, then we have a way to make this formula here now well defined, because now we have a way to extract finite quantities out of that. And the first thing we would like to know is to understand the correlators. So since phi naught is the source for the dual operator, if I take the functional derivative of my normalized action with respect to that source, I should get the one-point function. And it turns out one can do this computation exactly, and the answer is given over here. So the answer for the expectation value of the operator is precisely the term that appears over here. So the correlators of the quantum field theory are sitting inside bulk solutions at a specific order in the expansion. And in general, there can also be some terms, some local polynomial, which is related to kind of scheme dependence on the quantum field theory side. So to summarize this part, so there is systematic matching of the analytic structure of the gravity counter terms to those of the CFT, and that provides structural evidence for the duality that goes beyond specific examples. In the beginning of ADS CFT, there was a lot of kind of comments or criticism that this only happens because the examples were highly symmetric, and therefore the answer had to be of a specific form. But this type of matching is a structural matching. It's not specific. It doesn't rely on any symmetries. Secondly, we know that in quantum field theories, often some symmetries are broken by quantum effects. So this is called quantum anomalies. And so if the gravity side is meant to be dual to a quantum field theory, it has to have not just the same symmetries at the classical level, you have to find exactly the correct quantum anomalies, and that's exactly what happens in this case as well. So there are logarithmic divergences in this expression, which I didn't give. So if you keep going further down, you're going to find a logarithmic divergence. And this logarithmic divergence is exactly what you expect for a quantum field theory. And finally, when you have a normalized quantum field theory, that always comes with some finite ambiguity, which is called scheme dependence. This is related to finite counterterms, and you find exactly the same scheme dependence on the gravitational side. So in summary, we have exactly the gravitational computation gives exactly the right analytic structure. It gives exactly the right quantum anomalies and exactly the same, the expected form of ambiguities that you would expect for a normalized theory. So now from here, you can then keep going. So once you have computed the 1-point function, now if you want a 2-point function, you can differentiate. You operate with respect to the source to get a 2-point function. And then if you want a 3-point function, you need to differentiate twice and so on. So over the last 25 years or so, this has been developed to a very high level. So we now understand how to compute any correlator we might be interested in. So here I illustrated the method with a scalar field, but exactly the same way works also for all other fields, in particular for the metric. Actually, historically, the example of the metric was the first one that we did. So if you have a space-time which is asymptotically under de Sitter, there are results from mathematics, from Pfefferman and Graham from the mid-80s that you can write the metric in the form I indicate over here. Again, Z is the radial coordinate, and this metric here has an expansion for small z, which is of that form. And if we're in 4 dimensions, then this has 2 independent pieces of data. So this blue piece is again the analog of the source, and the source in the metric in the couples to the energy momentum tensor. So correlators that you obtain by differentiating with respect to G0 will be correlation functions of the energy momentum tensor. And then there is this red piece, which is again not determined by asymptotic analysis, but it is determined by in the full solution. And these are the 2 independent pieces of data, which are the analog of phi naught and phi tilde that I had for the scalar field. So now from here, you can see now how holography reconstructs a bulk space-time. So the Linux term G0 is the background where the 3-dimensional CFT lives. And then the subletting piece is related to the energy momentum tensor of the dual CFT. So with this data, we now have this asymptotic analysis, this asymptotic behavior, and then there is a theorem that these 2 pieces uniquely specify bulk metric. So if you're given the quantum field theory in 3 dimensions, this is going to give you a 4-dimensional, asymptotically ADS 4-dimensional space-time. Okay, so that finishes the introduction on the holographic dictionary. Are there any questions before I move on to now the issue of holography and entanglement?
Professor,
there is a bit of echo.
Take the questions at the end of the session.
Okay, that's all. That's completely fine. Yeah, we can have the questions at the end. Okay, so now let's move to the issue of quantum entanglement. So correlation functions are, of course, very interesting object. Correlation functions of local operators are very interesting objects to discuss, but they're not the only interesting computables. For instance, there are long-standing questions about black holes. What happens when you fall in the black hole and the black hole subsequently Hawking radiate? So we need to understand whether there is entanglement, quantum entanglement between the interior regions and the outside. So there's suddenly high interest in trying to understand holographically how to quantify entanglement. So quantum entanglement is also a key to data manipulation and storage in quantum computing, which might become crucial new technology in the future. And so let me give a very brief introduction. So suppose we have two subsystems A and B, and we can only measure the system A. So if these two subsystems A and B are entangled, this means that we cannot determine the state of A completely by such measurements. And the entanglement entropy counts the number of entangled bits between the two different systems. So to see the same thing in a picture, so we can have our quantum field theory in D dimensions, and we have areas A and area B, and a density matrix that specify the quantum state. So now we can define the reduced density matrix by tracing out all the degrees of freedom which is outside A. And then the entanglement entropy is the von Neumann entropy of this reduced density matrix. So, so if you want to understand entanglement, or at least start to understand entanglement, one of the things we like to do is we like to understand how to compute this quantity. So this quantity, it turns out, is very hard to compute in quantum field theory, but it's relatively easy to compute it holographically, because in holography, that now acquires geometric meaning. So again, this is the space where my quantum field theory lives, but now I have an additional direction because my space-time is asymptotically ADS. And there is a holographic prescription to tell you how to compute the entanglement entropy between A and B. So the idea is that you now look at minimal surfaces that are homologous to A, but go deep in the interior, and then you compute the area of this object, and then the entanglement entropy is simply the area dividing by 4G. So a formula which is familiar from black holes. And black holes, we have here the area of the black hole horizon, where in this context. So if we give it an area A, then this curly A is the area of the so-called Ryuta-Kanayagi surface, which is the minimal surface, which is homologous to A. Now, if you try to compute this in ADS, then you have similar issues as with the computation of the on-shell action. You still need to regulate because naively it's infinite, and it's infinite for the same reason. Kind of ADS has infinite volume. So as you go to the boundary of ADS, which is where the surface lives, you have an infinite contribution from the near the conformal boundary region. And you can quantify this in the same way as I did earlier by putting a regulator and then computing this entanglement entropy in the presence of that regulator. And the answer is given by an expression that I give over here, which again looks similar to the expression I had earlier for the on-shell value of the action. And again, the same way as we discussed earlier, then this expression here is exactly the expected form that for a CFT. In particular, there is a linear divergence, which is proportional to the area of the boundary of the diagonal surface. And that's exactly what we expect in the local quantum field theory, because in the local quantum field theory, infinities are local, and they're going to be localized in the boundary of the area. And similarly, there are coefficients which are again depend that diverge logarithmically, and these are again related to quantum anomalies. And the The other thing that we need to keep in mind is that, as we increase the size of this area, we kind of go deeper and deeper into the space-time. So this gives us a sense in how to probe the interior of the space-time. So then one could try to use now, so we've seen how holography geometrically quantifies quantum entanglement. So this gives a link to kind of quantum information concepts. I would like to utilize this new tool. In particular, a few slides ago, I discussed how to reconstruct the manifold near the conformal boundary by giving information about the quantum field theory, giving the quantum field theory data, namely the background metric and the stress energy tensor. And then one can ask whether you can now reconstruct generic regions using entanglement entropy. Can we reconstruct the geometry if we know the entanglement entropy? Or in other words, can extremal surfaces be used to reconstruct a metric? So this is a very interesting mathematical question, which is actually very active. There's a lot of activity in mathematics, and there are partial answers to this. So reconstructing the geometry is challenging in general, unless there are additional symmetries. And again, it's an active question, and there's still many open problems, especially when there are horizons and time dependence. And there's a long list of people that have been contributed and still contributing to this topic. So I will just sketch some of these ideas in the next few slides, and then we'll move on to kind of do a bit of kind of a bigger kind of grand synthesis of these ideas. So space-time reconstruction is related to a so-called renormalization group in quantum field theory. So in quantum field theory, someone could ask, if you have holography, okay, the quantum field theory lives in the dimensions, what is the additional direction? How do you understand that the space-time has one direction? And the answer to that question is that quantum field theory has different properties at different energy scales. And then you can think of as, stacking together the quantum field theory at different energy scales and making an additional coordinate. And that's exactly how ADS-CFT works. So the additional information about how to go from quantum field theory in one dimension to higher dimensions is obtained by stacking together the quantum field theory at different energy scales. Now, quantum field theory also has a property that as you go to kind of low energies, then you sort of get a coarse-graining description. So you can start from here from the UV, where it looks like, you have two cows, and then you go down, and then suddenly, in a sense, the two merge together because you don't have the resolution to see that you have two cows. You only end up with, looks like you have one. So you can have a different description depending where you are. So that's how, in a sense, that the additional direction is reconstructed. So I could try to now combine this idea here with this quantum information theoretic perspective. So this process of cross-graining is also very similar to cross-grained descriptions of interacting qubits. So you can think of each qubit as represented as a node in a network, and then you can have interactions. And then you can start cross-graining using a network. So this is an example of a network. So we can have our qubits here, and then the squares are the interactions. And then, so you start from here, then they interact, and then you cross-grain. So these red triangles are the cross-graining. So you go from kind of 2 qubits to 1. And now again, they interact, and then you cross-grain and so on. So you go to a more coarser description as you go further down. So this cross-graining has very similar features with this renormalization group flaw. And one may question whether they're one and the same thing, the different sides of the same coin. And this is an idea that has been pursued in the community. So So the interactions and the coarse graining, of course, depends on the tensor structure of the network. What are these links? When you write down mathematical formulas about the links, how do you contract the different qubits? And the natural question is whether one can choose tensors, these interactions, so that the coarse graining reconstructs a hyperbolic geometry, or rather a discrete version of hyperbolic geometry. And the answer to that question is yes, as provided by this for authors. And the idea is that you can use pentagonal networks to construct a hyperbolic plane. So again, here you can see it also from the future. It looks very similar to the Esler plane I showed you earlier. And now the coarse graining is interpreted as moving inwards, so as moving towards the interior. So to make this a little bit more precise, so here I have the hyperbolic plane, and I have tessellated this with pentagonal tiles. These are kind of the blue sides with a pentagonal. And then in the center, I have a node. So this node represents a logical qubit. And then we have the black lines that go between the nodes that relate to different nodes. And these are called physical qubits. So one can then think of the ADS-CFT correspondence as a version of an error correction code. So you have a direct link between these geometric ideas we have been discussing and quantum information concepts. So in particular, you can see from here, so the arrows indicate how the information is pushed from the center towards the end. And then the deeper we start from let's say if we start from here, we have a specific access to the boundary. So, and the deeper we go to the space-time, the more access we have to the boundary, or the other way around. The deeper inside the space-time, the more of the boundary is required to recover information. And this type of picture is also completely consistent with this Ryuta-Kanayaki relation that I showed you earlier between entanglement entropy and extremal surfaces. Again, if you draw here extremal surfaces in this picture, then you can quantifiably verify that gives the entanglement entropy associated with this network. Now, there's still a lot of things still need to be done. So more generally, networks can be described by simplicial complexes, and then this hyperbolic network geometry emerges naturally if you grow to bigger and bigger simplicial complexes. So to some extent, we find again some sort of universality that we expect from the normalization group flaws in quantum field theory. So this is a very active field of research, and there's still a lot of open questions, especially if we move to kind of Lorentzian time evolution and the emergence of non-hyperbolic geometry that we expect in a more general context. So this is still a work in progress, I would say. Okay, so to briefly summarize what I had so far, I started with a general introduction about the holographic dictionary, and I told you how you can use correlation functions of local operators to reconstruct the bulk space-time. And then we move on to kind of quantum information topics. We describe how quantum entanglement is described holography, and how we might be able to view the dictionary itself as a quantum error correction. So from this second perspective, the very structure of the space-time is encoded in the quantum entanglement of the different states in the dual quantum field theory. So in a sense, the quantum entanglement tells you what is the space-time in one dimension higher. Okay, so now in this last part of the talk, I'll try to now use the set of ideas in the context of early universe cosmology. So here we are. So we are out here, And this is kind of, this direction here is a time direction. And we know that as we look back in our history, we can map the history of the universe using Einstein equations. But when we arrive at very early times, then Einstein equations stop to make sense because we are in the region of very high curvature. So in a region of very high curvature, you need to use a quantum theory of gravity. So this is a place where the ideas of holography should be fruitful because allow us to use both quantum mechanics and general relativity at the same time. And now this region, what happens in the physics here, left an imprint in CMB, which generated a little bit later, which we observe now. So not only we expect to be able to say something about the early universe, but potentially this is observable by satellites. So in holographic cosmology, we like to describe our four-dimensional universe holographically, and this means by providing some three-dimensional quantum field theory with no gravity, and also a dictionary that relates quantum field theory observables to four-dimensional observables. So this is a topic, goes back to 20 years. The things I'm going to show you now are based mostly on work I've done with McFadden and Psovsky that started about 15 years ago. So why would one want to use such a framework? So first of all, I think one of the main points is that these models are manifestly consistent with quantum mechanics because they're based on quantum field theory. General relativity emerges when the quantum field theory dynamics become strongly interacting, but the models themselves are well-defined even when traditional general relativity breaks down, and that includes also this initial singularity, what happens kind of over here. It also has a natural explanation of the arrow of time, which I will mention in a minute. And finally, it provides an excellent fit to CMB data. So this is a plot from a paper from 2017. So this is the usual plot of kind of the Planck data with the different peaks. So here, there are two curves. One is kind of the traditional explanation with the so-called lambda CDM model. And there is also a second curve, which is the red one, which is holographic cosmology. And the black dots are the Planck data. And as you can see, this new models fit the data equally well as kind of more traditional models. Okay, now holographic cosmology offers a kind of drastic reformulation of the physics, and cosmological evolution is now mapped to inverse renormalization group flow. So here is our universe, started with very strongly coupled gravity, and as time moves on, becomes weaker and weaker. And on the dual side, you have a kind of field theory, which now the future is the UV and the past is the IR. And then the evolution here is described by inverse this renormalization group flow that I described earlier. Now that connection on its own also allows for an explanation of the arrow of time. So one of the properties of renormalization group flow is that they're monotonic. And this monotonicity explains why we have an arrow of time. Another property of renormalization group flows is that you have more degrees of freedom in the future than in the past. And this is one of the explanations people put forward for the fact that the arrow of time is entropic. So that also connects with this. But if the arrow of time would be entropic, then I would say, why did we start with a very low entropic initial state? Then again, that comes now from the universality of infrared dynamics, where initial conditions are completely natural because they're universal for all theories. So finally, let me briefly go back to the initial singularity. So now, again, I give the same diagram. So again, this direction is time. So early time means on the dual quantum field theory in the infrared of the theory. So now if you want to understand the resolution of the initial singularity, you need to understand whether the quantum field theory is finite in the infrared. And indeed, in one of the holographic models that discussed in the previous works, we're able to prove non-perturbatively using lattice quantum field theory methods that the theory is non-perturbatively infrared finite, even though naively you would expect the theory to have infrared divergences. So there is a non-perturbative mechanism that resolves the initial singularity. So what is the picture of a holographic universe? So, I mean, we live way up here. I mean, clearly right now we perceive a four-dimensional universe. So I would say we live in a geometric phase. And the geometric phase goes up to the point where one would say is the kind of the hot Big Bang singularity. But now that singularity now resolved holographically. So you have a non-geometric phase, which describes what happened before that point. And now the time evolution of the of this non-geometric phase is the same as the renormalization group law and the dual quantum field theory. And then the correlations that we see in the CMB, they just come from correlations due to the correlation functions of the energy momentum tensor of the dual quantum field theory. And you can make this completely, you quantify this completely and compare with data. And that's how we got kind of this type of fit by using this, by quantifying this type of ideas. So at the end of the day, the entire universe, the way kind of we see it, originates from this three-dimensional theory. And this theory, the way the geometry emerges, is closely related with quantum entanglement, which explains the structure of space-time. That's in a sense the big picture. So let me now kind of finish with a brief summary. So I think holography gives a deep relationship between topics which appear to be very different, kind of relates gravitational and non-gravitational physics. And the space-time itself is reconstructed from a quantum field theory information. And the blocks of space-time may be thought or be reconstructible in terms of some quantum error correction code. Okay, thank you.